Hi guys, welcome to the channel Code by Raghav, and in this video we are going to solve the question number 162. Find peak element. It's a medium type question and it has been asked by many companies interviews. As you can see, they are big name also: Amazon, Apple, Google, Microsoft, Roblox, Uber, Flipkart, Visa, Zepto, Zoho. So it is very interesting question, and this question changes our binary search definition a little, and let's see what it changes, and let's see how we can solve this question. Let's read the statement. So we have given a zero index integer array nums. Find a peak element. What is a peak element? We have given the definition. A peak element is an element that is strictly greater than its neighbors. Means, what is neighbor? This is your ith index element, then I minus 1 and I plus 1. These are your neighbors. And we have given nums of I will be not equal to nums of I plus 1. So it will distinct. So it will always be unique. Nums of I is not equal to nums of I plus 1. So, and return its index of the peak element. If the array contains multiple peaks, return the index of any of the peaks. You may imagine that nums of minus 1 equal to nums of n. In other words, an element is always considered to be strictly greater than a neighbor that is outside the array. Okay, so you must write an algorithm runs in O of log n time. So O of log n, what's the approach that works on O of log n time complexity? It's only the binary search. But we have learned so far the binary search definition that we need a sorted array to apply the approach binary search. As you can see, 1 2 3 1, it's not a sorted order, and if you try to solve with by doing the sort, so you will be mixing up the indexes. You have to return the index here, and as you can see, why is the 2 is the output, 2 is the index, 0 1 2 3. So 2 is the index of the 3. As you can see, 3 is greater than both its neighbors. So we have to find the peak element. To solve this, think of it like you are doing a trekking in a mountain hilly ranges. So let's say it's a mountain and you are trekking here. So when we when we go upwards, means we have to find the greater element. If our next element is lower, then it means we are going the downhill. If the next element is bigger than the ith element, the I plus 1 is bigger than the ith element, it means we are going the uphill. So that's the important point to solve this question. Now let's see how it changes the binary search definition. So as you can see in binary search, let's take this example. What in binary search, other than the sorted array, what's the main function of binary search? It it removes the it halves the search space. It eliminates the search space by half. As we know, we find the mid by doing the formula L plus H by 2, by halving the search space. That's why we got this O of log n time complexity. So we have to do the same, and let's implement the binary search in this. Let me write the indexing. If you apply the binary search, let's say L is your low is your 0 index, H is your n minus 1th index. If you found the mid, so you will get this mid 1. Then you will ask, point is then this point comes. If your next element is greater than you, is greater than the current, if the mid plus 1 element is greater than this mid element, that means the peak element will be on the right half of the array. Means we are going uphill. Our next element is bigger than the mid element. So we have to eliminate this left search space. So that's the functionality of the binary search. So we have learned in this question that it does not need that array should be sorted to use the binary search. Binary search main application is not the arrays has to be sorted. The application of main application of binary search is it halves your search space. It eliminates the unnecessary search space. So as you can see, our mid element, that is 2, is less than the mid plus 1. 3 is higher than the mid plus 1. So what we will do, we will remove this search space and move our L pointer to mid plus 1. And now next mid, what we get, this 2, the new mid. Now we see, is mid element is less than the mid mid plus 1th element? No, it is not. Means we are going downhill. 3 to 1 we are going downhill, or 2 to 3 we are going uphill. To find the peak element we have to go to the uphill. So why we go downhill? So we have to remove this unnecessary search space, and we will h equal to mid. Why h equal to mid? We have done so many questions using why we doing h equal to mid, because this mid element can be the peak element. And in the question it has already been said that it can contain many peak elements. Now we got this L and H on the same position, so the default template of binary search is applied the less than equal to H. If you apply it, so you will stuck in a loop. So why stuck in a loop? Because if you find the mid, it will get 2 again, and then you will again continue. Is mid plus 1 element is less than the mid? Means is mid element is less than the mid plus 1? No. So we remove the right search space, then we do the h equal to mid. That is again this condition. So we will stuck in a loop, so we will remove this left less than equal to h. So that's our approach. Then we will simply return the L or H, whatever you want, because both are in the same position. So let's try to solve it fast and let's complete the video. L equal to 0, high equal to nums dot size minus 1. So what, while low is less than the high, int mid low plus high minus low by 2. If nums of mid is less than the mid nums of mid plus 1, means we have found we had found that 2 is less than 3. Our mid is less than the mid plus 1. Yes, means we are going the uphill 2 to 3. So the peak element will be on the right side of the subarray. So we have to remove this left side subarray, left side search space. So we have to update our low. So low will become mid plus 1. Else we are going downhill. Instead of going the downhill, we will update our high equal to mid, because mid can be the peak element. Return low, mid, low or high, whatever you want. Let's run this. We have passed the test cases. Let's try to submit it. Our solution is accepted. Time complexity is O of log n. We have implemented the binary search, and space complexity will be O of n. We have not used any search space. So that's it for the video. Thanks for watching. Make sure you hit like, share and subscribe. Thank you.